laughing. It's okay. These are kind of like emergency coffee. I think I'm literally coffee addict. I mean, it's like I have it everywhere. In my car, in my bag, in my office. Yeah.
And Space Science Institute in Daejeon. There are lots of stories I could regale you with, but I will not then leave time for the talk. And so, again, welcome, Arman. I look forward to your colloquium. Thank you.
So, thank you very much, Tarun, for a nice introduction. I'm happy to be back to RI maybe after 20 years. Because I gave a JEST interview here. So I did a JEST exam in 2001. And in fact, I was offered by RI at that time with Professor Sridhar, which I just realized that he is retired now. And but you know, he knew that I'm more into the conventional cosmology. So when I got an offer from IUCAA, I stayed in IUCAA. But I kept good relationship with people here. So. I remember that Shiv and Biman, you know, they have been there from old days, and I'm very happy to see them still around. And of course, many new other faculties. I'm also happy to see that the environment is still very cozy and very friendly, and you know, which I think is important for science. So, in short, I'm happy to be here and you know, to discuss it with you guys. And thanks to Professor Suradip to invite me. You know, he was my mentor, and basically I had I was lucky to have one of my key collaborators, Tarun as one of my key collaborators during my career, and my main mentor, I would say. You know, someone who really helped me to make interesting and important decisions. So I hope that he can be also very useful for many young students here, and because he has a very good leadership skill, I would say, which is important aside being a good scientist. Okay, so I go to my colloquium, and I would be happy to discuss with people. Tomorrow I would be around, and also after my talk, so we can discuss. I've been working on quite many different things in cosmology and astrophysics, all relatively connected to each other, but not exactly connected. So you might find part of it interesting, and whatever you find interesting, you know, we can discuss by email or you know, even while I'm here. So yeah, the talk is about the status of the concordance model of cosmology, but first few slides at what is the standard model. Cosmology has become a kind of a science, or let's say precision science. When we could have theoretical works, we could have high quality measurements by building good instruments, and also we could develop statistical techniques to combine the data and get information from the data to basically test the models which we have. So practically cosmology was not even a science, let's say up to 60, 70 years ago. You could have whatever model you want, and then since there was no data, you know, it was very difficult to falsify different models. But you know, things changed, and we had various different observations. We could observe the universe in depth and in area and in different wavelengths, and then we could come up with the standard model of cosmology, which established basically not long ago, around 1998, where people could discover acceleration in the expansion rate of the universe. Basically, there were hints of that, you know, from early 90s by looking at the large scale structure data. But supernova type 1a as a standardized candles were the ones who somehow not confirmed, basically they rule out the standard model of that time, which was the standard core dark matter universe. So this lambda CDM model, or standard model of cosmology, now is about 25 years old, 24 years old, 23 years, basically it's the 25th anniversary. And it's a model which can be described phenomenologically by just 6 parameters. So we can assume the initial condition, which basically is about seeds of fluctuations, to be a power law, and the power law can be described by just 2 parameters, ns and ns. AS is amplitude, ns is a tilt. We need to know when the reionization, we have the epoch of reionization. We have Hubble constant, which is a very key important parameter in cosmology, which is about rate of expansion where we are now at the redshift 0. We have dark matter, which we assume it is cold and weakly interacting, so we can describe it by just 1 parameter, which is its density. We have dark energy, which is another density, and we assume it is a cosmological constant, which has the coefficient of a set of -1. We have baryons. Baryons are what whatever we see in the universe are made of. And we need to put everything in a framework. So we know that the GR is beautiful, is elegant, and is working pretty well. And then when we have GR, and then when we see that the universe looks isotropic and homogeneous, we can come up with a metric, which it is a Friedmann-Lemaitre-Robertson-Walker metric. And so we have this metric, and then we need to assume what's the curvature of the universe. So we assume the universe is flat, because flat universe is also very well motivated by simplest models of inflation, single field inflation, slower inflation, which at the same time predict power law from a premodel spectrum. So it's a nice model, but we should understand something very important, particularly for people who are not in cosmology here. A standard model of cosmology is not something that we derive fundamentally from some basic things in the physics or theoretical physics. It's a combination of assumptions. The fact that lambda is dark energy, or dark matter is cold, or we have FLRW, these are all based on the assumptions which we assume. They are reasonable assumptions, as I will get to, but these are assumptions. So there is nothing fundamental about that. And the model has been working pretty well. I should modify my slides. I gave this similar talk just a couple of days ago, which was 2022. Now we are in 2023. But the model, something like more than 20 years after the discovery of the acceleration, now we have about more than 1,000 type 1a supernova, which are standardized candles. What do I mean by standardized? Means that these are particular stars that when they explode, we can have a reasonable estimation of their brightness. So they are like a bulb that we know how bright they should be. And since we know how bright they should be, wherever they are depends on how visible, how much flux we see from them, we can estimate the distance. So they are very useful to measure the distances in the large scales in cosmology. So we see now that now we have a large compilation. We can go to the pretty high redshift, and everything seems fine with respect to the standard model of cosmology. We have cosmological background, which is about the fluctuation in last scattering surface when the universe is pretty young. The latest results which we have from the whole sky observation again shows a very nice consistency between the standard model and the CMB. And again, let's remember that about 25 years ago, we barely had the first acoustic peak. And this is the time that actually I started to do cosmology. When I started the project with Tarun, there was no WMAP. It was the boomerang and maxima were the state-of-art observation, and there was supposed to be a revolution in cosmology by having cosmological background data from the WMAP, which was revolutionary. So it was not as good as this, but we could clearly see the first 2 peaks and some of the third peak. So Planck was the next satellite, which was launched by the ESA, and it's a very beautiful instrument, and many people worked on that, including Tarun himself. And so we see that the standard model, when we get residuals, we can go to the very large multiples, which are very small scales. And when you get the residuals, everything seems to be very consistent with the predictions of the standard model. As another important cosmological observation, large-scale structure, which we basically map the galaxies in the universe. We measure the redshift by doing a spectroscopy. And so we have their distribution and we have their redshift. So this can give us also lots of information that how galaxies are distributed at different redshift bins in the universe. And this distribution can help us to get valuable information. And one of them is the standard model seems to feed the data pretty well. And so all these assumptions looks working pretty well. So a standard model of cosmology is a combination of reasonable assumptions. So I'm adding this reasonable here because it's not just like a random assumptions. When we talk about isotropy and homogeneity, it's because when we put our telescopes in different directions, we see that the universe looks the same. When we look at the cosmic wave background, we realize that, oh, it looks the same. So assumption of the isotropy is a very reasonable assumption, and we have not seen any violation of that. The same thing with the homogeneity. When we basically do tomography, we put the galaxy, we realize that the distribution of the galaxies look pretty the same in any direction which we look at. So that allows us to have GR, and at the same time we see that the GR has been passing one test after one test at different energy scale, at different length scale. So having GR and homogeneity and anisotropy of the universe give us this chance that yes, FLRW is a good metric. The same thing for the flatness. When we see that where the first peak of the acoustic peak of the CMB are, that is again some hints that, okay, it looks like the simple inflationary models works well. So we can have the power form of a model spectrum and the flatness. And the same thing as we saw, that cosmic constant can be a reasonable assumption for the dark energy because it's working pretty well. But there is a but. The point is that after the first release of the Planck data in 2013, when scientists start looking at the derived cosmological parameters, they realized that the Hubble parameters, when you feed the standard model to cosmic microwave background data from Planck, which now can go to the higher multiples, much higher than the W map, can predict the value of Hubble constant to be 67. But what is important here is the uncertainties which we have around these numbers. So this 67 was consistent with the expectation from the W map, which was 70. But W map had a larger error bars, and Planck now has a tight error bars. And these tight error bars from the expectation of the Hubble parameter, which we got from the Planck, when we compare it with the expectation of when we derive Hubble parameter from the local observations from the Cepheids and the supernova, we realize that, okay, these two are not matched. These two numbers are very close to each other, but the fact is that their uncertainties shrink to smaller numbers and their inconsistency grows. So this is some of the way that we can look at this, that by 2020, the Planck final release was 2018. There have been some changes in the likelihood codes, but nothing drastic. So the Planck basically come with a 67 plus minus 0.7.8, a very tiny error bar. And then we have the local measurements, which now they are stuck around 74 plus minus 1. And now these two values are at more than 4 sigma tension with each other. So if the error bars were large, things were fine. You could say, okay, we have a... So now the precision reached to a level that we really need to understand that what is really going on and why it is 67 and why this one is giving 74. And which one is correct? Because both cannot be correct. Yes, Tom.
And all?
I will show one slide almost
Okay,
at the end about
later.
that. But they are like a centralist. They are fine with everyone. So I have a figure about them. Yeah. So at the moment, the ones which have a bigger role, they are basically are not consistent with each other. But new measurements are coming. So in the end part of my talk, I will get there. So it is not only about H0 and CMB. There are some other tensions that one can find here and there. For example, one of them is about when we look at the BAO from the Lyman alpha forest of the barren acoustic oscillation from the large structure observations, and we see that this Lyman alpha BAO expect a larger value of matter density and larger value of Hubble parameter. And when we combine different data together, we see that when we just add Lyman alpha This basically shows kind of an inconsistency when we don't have that. Another one comes from the weak lensing shear that, when we feed the standard model to the weak lensing data and cosmological background from Planck, we see that they barely, overlap at 2 sigma with each other. So there look to be some kind of a combination of various tensions there between different observations that the standard model individually fits well, but not in a combination. Now, how to go beyond the standard model of cosmology? So I classify 3 main approaches, 3+1 main approaches. One is that, first of all, to validate that there is really something going on. To do that, one way is that to find deviations or features beyond the flexibility of the standard model. Basically, we find that data suggests something that the standard model cannot predict. So this is something very general. It doesn't matter if it's cosmology or astrophysics or condensed matter. Whenever you have a model and you have a data, if you find that your data suggests something that your model cannot cover, that's basically a very important thing. And those features are important to rule out the model or to validate the model. Another one is that if we have a litmus test or null tests are statistical approaches which we zoom the statistical power to say yes, no to a hypothesis. So we have a hypothesis, and a hypothesis basically predicts something, and then we say it is consistent or it is not consistent. And the third one, which is the most easiest one to do, is basically finding tensions among independent data. Basically, you have a model, you fit it to different data, and if you end up in different part of the parameter space, then that's a signation of the tension. It means that your model fit this data well, but they are not matched with each other. These contours are not really overlapping. But we need to find a way to quantitatively to evaluate the level of the tension. And there are statistical methods to do that. Sure. Yeah.
These various tensions come from, can you, for any one of them, can you say this is measured because there's a limited range of redshift values associated with each of those measurements? Or, for example, with say the BAO, there is sort of a range of, what I'm trying to say is that are you exploring possibly different redshift values with each of these experiments, or are they sort of spread over the entire values of redshift?
So actually people are exploring everything, but in this plot, maybe I would like to focus mainly on this one and this one, because in this one there are assumptions involved. Okay, there are assumptions involved. So I personally may not really take these things very seriously, because there are some assumptions from CMB or a standard model leaked inside the whole pipeline. But this one is very clear. We have a standard model, we have Planck, and we are fitting it and we are getting it. And these are just local measurements. So the red ones are more or less local measurements with some up and down. Yeah. So the main ones are certainly showing tensions, and the other ones, one can interpret. They assume that they are basically model independent, yeah. Or this is, again, people are investigating, but more or less one can argue that they are right. There are some very exceptional models that, they can breach to some of those assumptions, but there are still some assumptions, but they are more or less robust. These are more about the behavior of how Cepheids and how supernova type 1a behave, yeah.
And that's small redshift.
They are very local. They are very local. They are redshift less than, let's say, for the H0, which is coming from the supernova and the Cepheids, the big part the redshift less than 0.01, and then the part which is contributing goes up to redshift maybe maximum 0.1. Yeah. Yeah. So aside from these three theoretical statistical approach, if for people who work on theory of phenomenology, if you can have a model, and your model basically works better than the standard model, that would be great, right? But let's not forget, the standard model is already, it's a very minimal model. It's only 6 parameter, no flexibility for dark energy, no flexibility for dark matter, everything is pretty fixed. So it's very difficult to come with a phenomenological model which can outrun or outperform a standard model, particularly when we deal with approaches like Bayesian evidence. So, as some examples of the litmus test is an old work with Alexei Starobinsky and Varun Sani, which we had in 2014, and we showed that this omega matter H square tension, which to us looks pretty interesting. At that time, we said that okay, it should be most probably a systematic, but this has not been practically washed out because the most recent compilation of the data also showed that still the quasar BO data predict a slightly lower value of the Hubble parameter at the very high redshift. When we look at some other ways to, for example, evaluate the tensions, these are work by the Gongbu Zhao and some collaborators, including myself and one of my postdocs at that time, Benjamin Louillier, that it was shown that, again, if you assume the model and you fit it to the different combination of the data, how it performs, and it was very clear that the lambda CDM model has problems with two data, particularly one is a Hubble constant, local measurements, and this Lyman alpha BAO. This one for us, for me and Alexei and Varun, was a good news because this somehow confirms that there is literally a substantial tension with the BAO data. But the local Hubble constant measurement seems to be also extremely important, which has been remained there till now. There have been other works which basically try to look for systematics. For the case of the BAO from Lyman alpha forest, as I said, the revised measurements didn't really change things much. The uncertainty is slightly increased, so the tension is about 2 sigma or slightly less than 2 sigma. But it is something there, then we have to wait and see what will come from the DESI and Euclid. From the case of the local measurement of the Hubble constant, things become slightly worse because the Shoes collaboration led by Adam Rees, now their H0 value, central value, shift even to the higher value. So it was 73.5, now it is 74 something. And there were also some alternative analysis, particularly the work by Follin and Lloyd was pretty interesting because when I talked with Lloyd, they did a kind of they had a very skeptical view towards the whole analysis, but they somehow didn't find anything much fishy in the Rees analysis. And so there have been people who try to reanalyze the Shoes collaboration analysis, and they're becoming more and more open to the community, providing all the information. But I would say that, so far, based on our knowledge of the physics, our understanding of the Cepheid and supernova, these measurements seems to be pretty robust. So now, we are dealing with a situation which is very complicated and looks like that we have multiple suspects. I mean, I got this frame from the movie by Alan Keller based on one of the Agatha Christie's movies that, typical, I don't know, this generation of Korean, the Indian students, but in my days or previous generation, I think Agatha Christie was very popular in India, right? And it's very challenging, the way that she was used to write the stories. Till the end, you didn't understand who is the killer, At the end, you could understand, oh, the murderer is the killer, and the murderer is the same person, just, So things can be very complicated. We don't know who is who and what is going on. So how to understand and how to basically freeze again this vanilla ice cream and resolve the tension, again, I can classify them in different categories. One is that some people say is statistical fluctuations. Those people are not saying much anymore because now more than 4 sigma, it would be very rare that we are just by random things is coming there. There's a group of people who talk that there should be systematics in one or some of the data. And if I have to bet my money on something, I would be in this category too. So I mean, if someone said that, okay, in 2030s, what would you say, how tensions would be resolved? It is evolving dark energy, going beyond the power law, or whatever, early dark energy, or systematics, I certainly invest on this one. And one hint for that is that because it is highly possible that these tensions coming from not only one, but multiple systematics, because we don't understand many of the data. And one of the reasons is that in some of the papers which I had with Shaolei and with Ryan, was that, it's very difficult to modify the standard model and resolve the tensions. So if there's a tension which is physical, probably you expect that, okay, if you modify some part of the standard model, you should be able to go one stage further and now have everything consistent. But this looks like impossible. It's very difficult to resolve the tensions by any modification we should make to the standard model, unless we really, really make a huge number of modifications in different aspects of it, which looks to be a bit unnatural. From a 6-parameter model, we suddenly jump to a model which may have many, many more degrees of freedom. Another one, which has been hundreds of papers written, is about extended models. Many of them claim that they are resolving the tensions or diluting the tensions, and which is fine, but I would say that the majority of them, extreme majority of them, are overselling. And overselling in a sense that, you know, in most of these models you have more degrees of freedom, and by having more degrees of freedom, when you fit your model to the data, you have larger contours, you have a larger confidence balls, and having a larger confidence balls, you basically have a better overlap. So central values are not shifting. You have more degrees of freedom, your contours are this much, but then they become larger, and then when you have a larger contours, then they overlap more, and they said, see, you know, we don't have now any more 4 sigma tension, but we have now 2 sigma tension. So this is the way that many of these models are resolving or you know, diluting the tension, which to my opinion, it's okay to do that, but let's understand that how they are resolving the tension.
Will you be talking about the kinds of systematics that may be there either in the supernova data or in CMP data or unstructured data?
I will not talk about that, no, but I will just mention them, yeah. I mean, those are completely separate, but important, extremely important. So, I will get there that why it is actually extremely important. And I say that our approach at the moment is that we try to compare different data in a model-independent way, and also getting help from the independent observations to see where we should look for the systematics.
And another for another, or one value of H naught and another for another, but you're just saying that the models are so weak that they accommodate them both? Is that what you mean?
Kind of.
Okay.
Yeah.
So
Yeah.
you're just, okay.
So
That's really not a resolution.
Yeah, exactly.
Right.
Yeah. I will show you some examples here. So now, let's go to the standard model and then look at the 2 main lines that people have been trying to, you know, attack or address the tensions, including myself and my collaborators. So the first one, let's go to the cosmological constant, if dark energy is lambda, and if we can play with expansion history rather than having lambda dark energy, if we can have other form of dark energy, evolving dark energy or early dark energy, and if we can really help to resolve the tensions. One of the papers which got lots of attentions, it was published in PRL by Mark Komnikovsky's group, Pauline et al., was about this early dark energy. That the idea was actually not new, it was there, but the overall idea was that we know that we can combine the information from H0 and RD. We can have a good constraints for H0 RD by combining some information. And H0 is a very late parameter, is the expansion rate at the redshift 0, and RD is basically early universe parameter, as I described here. And now if I have this value, let's say we know what it should be, and if I want to have a higher value of H0, then I should have a lower value of RD. And if I want to have a lower value of RD here, how can I do that if I don't want to play with the radiation density? The point is that if I increase the expansion rate, and this is basically Big Bang, this is the last scattering surface. It's a baryon drag epoch. It's a baryon drag epoch. Yeah, so okay, think of it, RD is this equation. Okay, so if I want to have it smaller value, I need to increase the denominator. But to increase the denominator, I should have to have a larger h of a. And Hubble parameter at the redshift of 1100 onward is highly dominated by matter density because it has the 1 plus z cube in it, and cosmological constant is constant. So basically, they say that if you have a substantial amount of early dark energy, let's say 10% of the contribution from the matter, that would be enough to have a slightly lower value of RD, but having a slightly lower value of RD, I can get a higher value of H0. And the model has more degrees of freedom. So by doing that, they basically claim that this can help. As you see, it's published in PRL, which is not easy to publish in cosmology. But there were works after that. There were people who were skeptical, but one of the works was Hill et al., which later shows that this model is not really solving things much by just shifting the mean parameter from 67.3 to 68.3 and having a slightly larger error bar because you have more degrees of freedom. So error bars from 0.6 now change to about 1.1, and mean value is slightly shift. So it's a reducing the tension, but it is not really resolving the tension. Still, it is far from the 74. It's not 4 sigma, but it is still about 3 sigma tension. Another way, which was, I mean, I'm showing some of my own work, was about late dark energy evolution. So, for example, here we introduced the phenomenological emergent dark energy, which is a model of dark energy that doesn't exist in the past and it just appears in the later time. So this model I had in mind for many, many years from the time which I was in England. And I was working on that to address the coincidence problem or cultural constant problem, that why cultural constant is so small. So idea was that let's having something which is very fine-tuned. This is something called fine-tuning problem at the Big Bang stage. Let's have nothing at that stage, and dark energy be something like an emergent late phenomenon, which is appearing as an effective way related to some other phenomenon. So I never get anywhere from theoretical point because I could not find any way, any critical phenomena which can basically address that. But for these tensions, I realized, okay, that might work, that, you know, I have no dark energy and then it appears, so it injects some energy to the universe. And it might work better than the standard model if Hubble parameter ends up to remain around 74. So it's a work with Shaolei, and the work it has a substantial different features than the lambda-CDM. For example, there's a work by the Holika collaboration, which compares some of these models. So PEDE has these characteristics that it can give naturally a larger value of Hubble parameter and having the similar value of the RS, which is similar to the baryon-Drucker point. So the model is not working better than the lambda-CDM model at the moment, you know, but who knows? If Hubble parameter ends up to be about 74 and its error bar shrink from 1.2 to, let's say, 0.5, then this model can be substantially better than the lambda-CDM. So it's like an investment for the future. Then we come with the generalized emergent dark energy, which is like a generalized form of that. Now he can accommodate this form, can accommodate both lambda and PEDE. So if delta is equal to 0, it gives you lambda, and if it is equal to 1, it gives you PEDE. For any value of delta larger than 0, it comes with the emergent phenomenon. So it basically means that any value larger than 0, dark energy is not existing in the past, and it's appearing later on in the universe. And the delta just showed how fast this transition would happen. So it can be a nice way to test this phenomena, this mechanism, if it is emergent or not. And when we test the model by using combination of different data, there is also pretty interesting that when we add everything together, we realize that, you know, the delta, basically the posterior for the delta is larger than 0. So it basically data support this emergent behavior with respect to the lambda.
Do you modify the Einstein equations or the nature of matter that you have?
It is just purely phenomenological. So
But what is the effect that it has, for example, on energy conservation or something of that sort?
So those conservation equations are there. Okay, so these are fine. Only I'm playing with the equation of a state of dark energy. So you can think in this way. That equation of a state of dark energy.
Oh, so, okay, just the pressure.
Right, relation between pressure and density.
Okay.
So it is a function of redshift. For the cultural constant, this W of Z is always -1.
Okay. So this is not those tracker models or those?
It's not a tracker model, no.
Okay.
It would tracker models are usually in the quintessence fields.
Yeah.
These ones, this one can have a equation of a state less than -1, which we call them phantom behavior. There are some theoretical problems with them, particularly when we are deriving the perturbations. I know that many theoretical physicists don't like equation of a state less than -1. But you know, it is a phenomenology, and we just want to first see that if data support that or not. So yeah, so the equation of a state is based on this. So if delta equal to 0, you see that this part will be vanish and it will be just -1. And 1, then it basically comes back to PEDE. So when we get to here, you know, this is a work which I did with some of the younger collaborators. And they usually said, look, you know, JEDA now have a Bayesian evidence of 6 with respect to the lambda. And this is usually what people usually make a big claim, that, oh, you know, the model is killing the other one. It's like strongly favored by the Jeffrey scales in the Bayesian evidence. But the fact is that we should realize one thing important, and is that the current tensions allow us to find models which are better than the lambda, but they do not really resolve all the tensions properly. So what I'm saying is that, yes, this JEDA model, which is my own model, you know, we work with the Shaolei, it works much better than the lambda. But, and even with the Jeffrey scale of 6, when we combine everything. But is it really resolving all the tensions? The answer is no. The answer is that, still my mean functions, mean values are not really shifted much, and I cannot really claim that I'm really solving all the problems. And this is something that we should really keep in mind. And I think everyone in the community should keep in mind. So just some very side notes, just maybe 1 minute for each. If you are interested about, how to do the model selection, particularly the most solid way is based on the Bayesian evidence. People use this BIC, AIC, which are basically not very interesting, not very correct even statistically, but Bayesian evidence is a very important way to compare different models. And Bayesian model selection is something which I think the most robust way in the whole physics and chemistry and different fields of science for the model selection. But it has, the conventional way it is used has some issues that one has to consider because it depends on the quality of the data and complication of the model. The scales that we decide how to address how one model is favored to the other one can vary. So I suggest you to look at this paper with Ryan, which we wrote last year. It's been published in M. Ross. The editor didn't like this, but anyway, they could not stop this. And this is another paper, again, last year we published with Hanul, my student. And this is also interesting to understand that the Bayesian evidence approach is solid, but only can find the better model among the existing models. So if you have 5 models, with Bayesian evidence, you can find the least wrong model. But it cannot tell you if all the 5 models are wrong. So this is, we did this challenge that we have 2 models to compare, PEDE and Lambda, but we generate the data, we simulate the data based on another model, which was the transition dark energy model. And then we said, okay, now you guys compete with each other. So both, and then we showed that conventional statistics, Bayesian evidence, it basically prefers lambda to PEDE at all different scales, which is understandable because lambda is closer to that model. But the fact is that the both models are wrong, and this is not what you can really expect from the Bayesian evidence to do that. So we come with this iterative smoothing validation approach, which basically we can, independent of comparing with the other models, but just having the data, we can say that it is right or wrong, or how wrong it is. So, it is interesting if you are interested about model selection and validation before model selection, which I think is very important, missing in the community, that before comparing models or testing or even fitting the models to the data, we should first validate them and says that, okay, if they can pass the validation. And that validation is something that you cannot do with the conventional Bayesian approach. Okay. So now I was talking about the dark energy as a solution, about the Hubble tension. This is a recent paper with Ryan. We are still with the journal for publication. This is an interesting paper because we said that, okay, now with having 1 or 2 degrees of freedom, we cannot really solve it. Let's give the model many degrees of freedom. So we assumed a hyperfunction we got from Chebyshev polynomials, and then we added more than 6 degrees of freedom on top of 8-parameter model of the lambda CDM plus, CPL parameterization for dark energy. I said, okay, now you guys try to fit the data. Okay, now try to give me H0 more than 73. So the result was very interesting and astonishing that even though giving such a high flexibility, we could not really get there. And a posterior for the Hubble parameter ends up, to give me very, very tiny consistency with 72, but it barely could get to 73. So then we conclude that, basically it's not possible to really solve the Hubble tension properly by playing with the equation of dark energy at the low redshift. By low redshift, I mean anything lower than redshift last scattering surface. So to our opinion, this is an important thing to think that, okay, what is really going on? And
anything after the last scattering surface, you can't have any new physics. Is that the claim?
well, if you want to play with the form of the expansion history, evolving dark energy model, yeah. That, I mean, what
Right,
you are saying that it cannot solve the Hubble tension.
I see. So they can't be, because there can be something leaking out of whatever the previous epoch, right? There can be semi-classical effects from, or You're saying that there's absolutely, the constraints on that are very strong. Is that what you're saying?
What I want to say is that no matter how much you play with the expansion history, no matter how much you play with the expansion history at the redshifts after the last scattering surface, right? Let's not forget that the age of the universe passed very quickly up to redshift of 2 or so, right? So the dark energy is a very late phenomenon. So many things which happened at that time is not really much important because matter density has a very high role. But practically, it is not possible to play with the expansion history and resolve the Hubble tension. And so it's one of those cases that we discussed about the von Neumann's story of the 4 parameters to fit an elephant. No, even if I add more degrees of freedom, still I cannot fit the data well. And these models cannot really give a higher value of Hubble parameter. We can have very exotic models, very exotic. I mean that the Hubble parameter comes to redshift of, let's say, 0.01. And then at the very, very early redshift, when there is no data, suddenly it jump up, right? So these are very exotic models which they cannot be realistic. But if I want to have some reasonable model which have a reasonable behavior, that would not possible. Yeah. So one can interpret this in a different way. Some people said, oh, good. So now we should go back to the early universe and solve the problem, which might be a reasonable approach. But one thing which I would say that we should not forget is that might be some systematics. There might be some systematics in any of these data which we are observing that, maybe, the way we understand cepheids and supernova or their combination, the way we are anchoring them together, the way we are looking at these samples might have some problems, and then that might basically lead to the high value. Maybe the way that we are treating with the other observations might have some problems. So anyway, now going to another way that we might be able to address things. And it's about the power law premodal power spectrum going to the early universe. So the story of trying to reconstruct the model-independent premodal spectrum goes back to many years ago. So this is my first paper in cosmology with Tarun Suradip, my PhD in 2004. It is my basically master thesis. And as you see, it's published after this one. That's one of what I was telling to people that Tarun was not very happy with me because I didn't understand how important it is to be the first in the community. And the Sarah Bridal and I think a statute group wrote that paper slightly few months earlier than us. But anyway, so anyway, these are very important things to understand how the seeds of fluctuations are. And this premodal spectrum, it basically tells you how the universe is basically going to grow, how the distribution of the galaxies and density grow in the universe. And the activity has been immense, in the community. The different methods have been developed, and while data support the background to be the power law to be consistent with data, but you see that you have other flexibilities. So one thing important here to address is that even though the power law is consistent, data allows you to have other form of premodal spectrum also consistent with the data. And these other models might be consistent with the data with a combination with the other background parameters. So for example, if I have this broken model can be consistent with the data, but not exactly the same background parameters as the ones with the power law. So for example, these are 2 parameters, but the matter density in Hubble for this model might be different than Hubble parameter for this model when I feed it to the CMB data. And this is a work that we have a group of the papers with Alexei Starobinsky, George Smoot, and Diraj, who was my postdoc now. He's in IMSC. That these models can be interesting. The group of Wift inflation model, and they can have a distinct form of the premodal spectrum, and they can basically feed the data with a slightly different background parameters. And this is something that we might basically think to address for the Hubble parameters. So the key point is that in the standard model, you have this premodal spectrum, and these are the background parameters. Together, they feed the data. Now, if I said that I don't want to have this assumption, I want to come with a different form, reconstruct it, or come with another phenomenological model, then these background parameters might be different. So, so how to reconstruct this? We can go with the Richardson-Lucey deconvolution. There's a series of papers, again, started with Tarun, going through the whole years till now. Till recently with Wu Yan, my postdoc, we are working on some regularization of that, using it for the image processing. We are even thinking to apply it on some medical imaging, which is an interesting way. That's one of the things I should talk with the Tarun to. Maybe, we can reinitiate some of those collaborations if the directorship here allow him. But anyway, it's a very solid method developed through the years, and it can basically work pretty well. And as I said, you know, we can now have this is a Richardson-Lucy which we developed with the Taron, and this one also with the Taron and Diraj later on, and this is a regularized one which now also have a control of the noise. So there is an application in image analysis, and looks a pretty interesting approach. But for the cosmology, what we wanted to do is this old idea, which again, I would say that the credit goes to Taron, because in this paper, we could show that if you go beyond the Fabio form of premodal spectrum, then the data allow you to have other background parameters consistent to the data. So we wrote this paper in 2013 with WMAP 9 while I was already in Korea, but I remember that we tried this in 2007. And we couldn't get anything. WMAP 5 data was not strong enough. Maybe Taron do not remember that. But my Markov chain could not really converge. You know, I could not say. So at that time, our conclusion was that even, you know, no dark energy model was consistent with data. So these contours were huge. But later data reached to the point that even if I give maximum flexibility to premodal spectrum, still it is not possible to choose any point in the parameter space and come up with a form of premodal spectrum that make it consistent to the data. So this space become limited. Now, in the case of the Hubble tension, what if we do a trick? So I go back to the old discussion with Taron, more than 15 years discussion, and we said that, okay, what if we fixed Hubble parameter to be 73, like what Adam Rees is saying, and I want to put my matter density of also what kids and CFHT and Des collaboration from Rick Lensing telling me. So I have a lower value of matter density, I have a high value of H0. Now I force my premodal spectrum, I project the problem premodal spectrum. Can you fit it for me? So to our surprise, the work done by Diraj, we show that yes, it is possible. And this is something very interesting because it shows that it is possible to have such a weird form of premodal spectrum, which can, in fact, give you the Hubble parameter and matter density at the different values. And now it is completely consistent with the Wick lensing and Hubble local measurements. So we didn't try to oversell it, that, oh, this is great, we are solving the problem, even though I would say that this is one of the works which I personally find it very robust. That, you know, there exists a form of premodal spectrum that can address many things. So some comments on the modified Richardson-Lucy. If you are interested in the convolution, you know, you can read these papers. These are pretty solid works. They have applications in other weird field of science too, but it's good to use them for cosmology. So a little more that, you know, with these features we find how many of them are useful, how many of them are not useful. So you can evaluate more on that. I'm not going much into this. But one thing which was interesting in this recent last year, which I was discussing with the Diraj and his student Akhil, was that we have the reconstruction, and after reconstruction we can go with the phenomenology, and after phenomenology we can go to the theory. We said that, okay, we have this reconstruction, but when you do the non-parametric reconstruction, it's like that you have 1,000 degrees of freedom. And people say, okay, that's, you know, you can fit even a dinosaur with that. But we said, okay, let's look at the useful part of the spectrum and come up with a phenomenological model with, let's say, 4 or 5 degrees of freedom and generate those features. And this is what we come. So we come with a kind of a reconstruction, which is basically have a phenomenological equation for it. And basically that could solve lots of the problems. So this phenomenological approach could basically show that, yeah, I mean, I can, by problems, I mean, there were some internal CMB issues, like this A-lens parameter, which I'm not going to details of that. The issue was that if you allow curvature with the Planck data, then, you know, the CMB data alone was basically saying that, oh, I'm not very happy with the flat universe. So, of course, there were different kind of likelihood codes, like internal politics of Planck. I'm not getting into that. But these issues were there. And we showed that this one spectrum basically not only can shift the Hubble parameter to the larger values, but also can address this A-lens and curvature parameter, as we see here. With our reconstruction from phenomenology, we are very well consistent with the A-lens equal to 1 and 0 curvature. Why in the case of the standard model, you know, both of these points, 0 curvature and 1 A-lens, is outside 2 sigma. So yeah, we had one spectrum which could address many of these issues, and at the latest stage with the Fabio Finale, we come with this theoretical implementation and implication, which if someone is interested, we can look at that. So it was first reconstruction, then phenomenology, then come up with a theoretical model, which can generate similar features. Okay, so current status, I think I would be slightly behind the time, but I hope it's not too much. So the problem is open. There are many tensions and there are various hints for systematics. As I said, if I want to bet, I bet for the systematics. There have been many models proposed, but none of them is convincing, okay, including the models which I proposed myself on dark energy. If one of them is correct, I would be very happy. But I'm not going to bet on them. Let's put it this way. If I have to bet on something and I gain something back, particularly if it's money, then I go for the systematics, not my own model or any other model. And one reason is that it is not possible to resolve all the tensions by having these minimal modifications, right? And that basically gives you a hint that, okay, maybe something is really fishy, which is not about the model. One thing extremely important, going to the question that you asked, that now it's important to look for the systematics and having a systematic way to look for the systematics. When we are talking about the systematics, we are talking about the unknown unknown. We don't know what we are looking for and where we should look for that. So one way is that, for example, to test independent consistency tests between different data. When we are reducing the number of assumptions, for example, this is an official STSS paper with Ryan before he leaves, which basically we try to test the consistency of the final STSS BO data and Pantone supernova compilation using Gaussian process regression. And show that, okay, these two data, independent of the model which we assume, they are consistent with each other. And if you could find inconsistency, that could be a hint in systematic in either of them. We don't know. But we found everything is fine. So the future perspective is that, yes, there is a high possibility of the systematics in different data. And to address this, we need independent measurements. And why to do that? Means that, okay, we have two data. It's like that you're going to a doctor. One doctor says that you have this problem. Other doctor says you have this problem. And these two are completely different. How can you trust any of them? Both of them are very legitimate doctors. You need a third doctor. You need a third opinion. You need a third diagnostic. And if the third doctor basically guides you to other direction, you might still, get more lean towards one of them, which I will get to what Taron said from the, your question about the TRGBs there too as well. That we need new measurements, and these new measurements can help us a lot to understand what is going on wrong and where. So this is about the TRGBs. So these are very solid. I would say that the physics of the TRGBs are better known than Cepheids and the supernova. They are more solid from the physical point of view. But we have a volume problem. We cannot go to very high redshift and, to observe them, we have to be patient. But at the moment, these guys are really centralist. They are fine with the high redshift estimation and fine with the Hubble. So I really hope that these guys take a side, either go in this side or go to this side. But that would be very interesting to see what TRGB does. Another approach is about the strong lens systems. This is something which my group has been pretty active in the last couple of years, is that you use the strong lensing of the quasars or supernova to measure the expansion history and the Hubble constant. And it is actually now becoming competitive. For example, there's a paper we wrote 2 years ago with Kai and Ryan and Eric, that we basically have 2.3% measurement of the Hubble constant in a model-independent way when we combine supernova and 6 strong lens systems. And this is something very interesting. This is something that means that we are getting there. We are getting close to which it can be competitive. The future astronomical surveys like a Rubin and Roman basically can be mind-blowing in a sense that, we are talking about the 1,500 supernova now. By the time of the Rubin, there might be about few hundred type 1 supernova every night, right? So in 1 week, we'll have more compilation of supernova than the whole astronomy till now, technically. And so you see that we can go to the order of 100,000 supernova. We can have so many strong lens systems, so many low redshift systems. So basically, the next decade, you would have loads of information which is coming and would help us to probably address many of these problems. So these are about strong lens systems. Again, this is one of the, yeah.
You will find more supernovae, but will it help go to larger redshift?
With the Roman, yes. With the W first, yes. So with the Rubin, we would have a big compilation in the intermediate redshift, but we would have also Roman, which is a space telescope. So Roman was mainly sold to NASA as a exoplanets survey. It's even in the exoplanets category, but it is extremely important for the cosmologists for the very high redshift supernova. Also, BAO from Euclid and DESI, we go also to higher redshift. So these are about the unresolved systems. As I said, there are some statistical analysis which is done, and my group is also very active. So the idea is that we want to try to find lens system. When these lens system are like that, it's easy to calculate the time delay and magnification. But if two light curves are on top of each other, and you see just something like that, that is very difficult to get the time delay and magnification. This is what, like in this case, that you have two light curves, and this is what you observe. And now you need to get that, oh, this is coming from these two. So you need to do some magic to get that. But this is possible in a very interestingly different way, dealing with the supernova and the quasars. If someone is interested, you can discuss. This is the main work which I did with the Satadru, who was a student in IUCA and worked with me, and now he got a Humboldt Fellowship in Germany. So he's going to work with the Sherry Seuss group. So going to the high redshift related to the expansion history, yes, supernova from the Roman can go, but also large-scale structure. Now we can observe galaxies in the higher redshift, different type of galaxies and tracers. And while we are here at the moment with the DESI and with the Euclid, we can go really high redshift with the scale of the distances much better than what we are now. I put Amir's picture here because the first author of this paper, but this paper was alphabetical. Okay, so I should say that he had very little contribution to this, but anyway, it's good to hire people whose name will end up at the beginning of the large collaboration papers. And because these are one of the key DESI collaboration papers that everyone knows with Agha Musa et al. And Amir, by the way, he understands that there is not much in academia. Now he's a data scientist in a big company in Seattle. Good for some student to know. So in the redshift distortion too, we can get some good constraints on the gravity. Things become much better very soon. Actually, DESI is ahead of the time. So I'm a member of DESI, and we find it more exciting because Euclid had some problems, but things are getting well. So one or two slides on gravitational waves. Things with gravitational waves are also getting very interesting. So these are like a forecast that the error on the Hubble parameter can reach to sub 2% from the bright sirens. There have been works which are basically that we can do cross-correlation of dark sirens with the large-scale structure data. These are from the Subodip's papers in the last 1 or 2 years that, for example, he used the, correlation between the gravitational wave data and DESI and SphereX. And we can get interesting constraints on the different parameters. But going back to one discussion we had today, here we should realize that the still cosmology background model is assumed, and still the bias function form is also assumed. So if you want to go beyond all these things, we have to be more cautious. Just one slide. It's a paper which I wrote a couple of years ago, very sensitive paper. It takes us 1.5 years to publish. In these kind of cases, I put myself ahead of my postdoc because we criticize some of these claims that you are going to have a very high precision estimation. And we put that, yeah, these are happening, but when you make lots of assumptions. But if you don't do that, for example, if my true model is this one, right? My true model is this one, and we assume lambda CDM to fit, let's say, very high precision data, then we end up in such points in the parameter space, which even, for example, in 2 sigma, we would be in the 2 sigma bias, inaccurate with a true model. We can do non-parametric estimation, so it's the next paper which we wrote, and so you can combine things and have non-parametric methods to control this bias. Okay, so just a few more slides about the future perspective. I discussed about the strong lensing, about the supernova, baryon-acoustic oscillation, about the primordial universe. This is a slide I'm using for many years. It was even in my PhD thesis. I think Taron should remember this. Still, we are the same page, right? I mean, it's still interesting that this PK, this PK, this PK is the same. And so we can use polarization data. We can use polarization data and have a good understanding of how primordial spectrum should look like. Next generation of the CMB surveys will hopefully come. I should talk again to people to see what is the status of the CMB Baharat, because the Lightbird has been going on pretty well, but CMB Baharat could be or still is one other good chance to have a space satellite for the CMB. We can go from 2D to 3D. Basically, from the CMB, now we consider the large-scale structure. It has its own complications. But one thing which we have been emphasizing is that when we deal with the 3D data, maybe it's better to go beyond power spectrum, which we are reducing the dimensionality of the data from 3D to 1D or 2D. Okay, so now why it is interesting, because now we have good computers, we have good machine learning techniques, good AI techniques, which now we can maybe study these boxes without reducing the dimensionality. And so this is an important point, that advocating against reducing dimensionality, which is a little opposite to what majority of the people are doing. They want to do things quickly and faster. We are saying that no, cosmology data is expensive. Let's sit on it, but do a proper analysis and you know, let the computer works and extract all information possible from them. So my last two slides. So what I find in the next 10 years will be important for cosmology is basically the cosmology versus systematics. That with the higher quality of the data, the role of systematics will become more and more prominent. What do I mean? Means that if you have a large, basically low precision, large uncertainty, little bias here and there is okay. We are still within the uncertainty. But if the precision becomes very tight, if you have a measurement plus minus 1, and then you have plus 2 bias, that would be a killer. If you have plus minus 10 and 2 inaccuracy, you know, it's okay. But if it is your accuracy become comparable to your precision, inaccuracy comparable, then that's dangerous. And that can come from not only systematics in understanding the data, but also if we make wrong assumptions. For example, now many of the cosmology pipelines are based on a standard model of cosmology. Lambda dark energy, Pavlov P-model spectrum, flat universe. And these pipelines, if any part is wrong, whatever we get out of it might also not be very correct, particularly when we test other models. So this is what we should be about. And the last slide, the standard model of cosmology looks fine, but individually, but there are tensions, and we need to understand what is going on. It gives space to the theorists, to phenomenologists to come up with alternative models, which is fun to do. But one thing which to me is very important is we should understand that the systematics might be the actual player here. And this systematics might not be only in the supernova or Cepheid data. It could be also in the way that we are understanding CMB lensing, or the way we are writing or BAO or redshift distortion pipelines. And these systematics can be of different nature. Systematics could be that you are making your pipeline based on GR, and then you are testing a modified gravity model. This is a form that one should not do. You should do the whole pipeline together. So these assumptions and systematics are something that we should take very seriously. And this decade would be extremely important, because we have surveys coming. You know, for example, DESI is ahead of the time. Soon by next summer, but this summer basically, we would have hopefully the first year data out. We have Euclid, we have LSSD, Rubin, we have Roman WFIRST, SKA, you know. Next decade, you would have Lightbird. So many information is coming. We have a SphereX, and this information would allow us to rigorously test the standard model. And it is important that we find something beyond that, because this is the talk which I'm giving more or less in the last 10 years, and I'm just modifying it with new work and new work and new work, but nothing really changed. Still, the standard model is the same standard model as when I finished my PhD in 2008. But if by end of 2030s, 2028 or 2029, still we are talking about the same standard model, the problem is that the governments would not give us money to go for beyond that. And that's why strategic planning is very important. Strategic planning is very important to look for the vision, what is to do. In my opinion, radio astronomy, for example, looking at the data which come from SK or gravity waves are basically very important future. That because independent of what is the standard model, these are the ones which are going to give us deeper to the universe and understanding not only about cosmology, also about astrophysics. So I think we are in a very special stage that, you know, we need to use our vision to choose the right path. And I hope that, you know, some exciting things happens in the next couple of years. Yeah. Thank you very much. If there are students, I would like them to ask questions. You know, that would be good.
I'll come back to the systematics again. You know, in case of type 1 supernova, now one doesn't know what leads to type 1 supernova. It could be accretion-induced collapse of a single white dwarf, or merging of white dwarfs, or maybe a third path. So what if, you know, these different paths lead to slightly different standard conditions? And what fraction of you know, different paths contribute to supernova at different redshift. Even that might, that could be major systematic, not knowing what the supernovas truly are.
I basically agree. Yeah, I mean, as I said, we don't know the physics.
That value of 74.
So, I mean, yeah, I agree that we don't know the physics of the supernova. I mean, and there are, there are lots of issues going on, right? There are lots of issues going on, and I would say that when we put uncertainty on any measurements, it's a very important thing, right? And one of the things which I personally could never understand in a solid way. I know what people are doing, and I know that that makes sense, but how better it should be that we can extract more precise information from them, that is something which I'm not very sure.
So until we know what those standard candles are, and is there a single standard candle, are you giving too much importance to the value of 74?
Well, this 74 is not only coming from that, because these are all low redshift. So there are few skepticism about the supernova. Some of them are coming back that they are basically time evolving, right? But many of these supernova are basically in the very low redshift, so people are assuming that they are of the same kind. But I basically agree. I mean, I would say that if someone, because it's not exactly my field, but if someone says that, okay, our understanding of supernova was heavily affecting this 74 which we are deriving, because we are anchoring them also to the Cepheids, which we don't understand them also not very well. I would not be surprised. It could be. Again, I mean, this is not something that I can defend, these numbers. This is a state of art, and that's what I'm saying. I would look more for the model independent, or look for the alternative measurements. That, for example, this work on the strong lensing, No, by model independent, I mean that, for example, when we deal with the quasars, lens quasars, these guys, we are basically the expansion history and the end of the expansion is at redshift 0. They are basically connected with each other, right? And because when we are dealing with the actual luminosity distance and what we get from the supernova is slightly different. With the luminosity distance, we know the distance in the megaparsec. Supernova just give you the relative distances. Now, when we compile them, and compare them together, and we are not assuming any model, to some level we can have a better non-parametric estimation of the Hubble parameter. But again, there are lots of assumptions are there. Like, for example, we are assuming the flatness. We are not assuming, flatness is still there. So, but the very local measurements of the Hubble constant, what like they are doing with the Cepheid and supernova, if there is something going on there, I would not be surprised. There have been skeptics. There have been people who have been criticizing the way things are done. But those people also have not been very also convincing. So I would say that, yeah, I mean, this is how it is. I don't think that, what you are doing is wrong or there is a way to do better. But I agree that, we need to understand things better. I mean, and if we don't, maybe we should rely more on the other sources. That's why gravity waves, neutron star mergers would be very important, right? Because they may have their own bias, they may have their own systematics, but at least it's a new measurement.
Since you've brought up this question of flatness a few times, if you did modify, say, a closed universe with positive k, still sort of compatible, because you can always have a very small curvature, which is positive. Is that something that one can actually put into the? I mean, is that out and out inconsistent with data, or is it something that people just haven't used or done?
Well, we do test flatness. Still, we do test flatness. I mean, one slide which I very fastly passed very early on. Oh, this. Which side I am? Okay, I'm here. Yeah. So. No, people, when they feed data, different models to the data, they consider flatness. And sometimes results are pretty surprising. For example...
Are you saying that when they're doing model building, they don't try different k values?
They do. But usually when they find it, for example here, this is very interesting, I didn't talk about that. So this is a paper by Eleonora Di Valentino, the Mercury and Silk, which very interestingly, it was there in the Planck papers. You know, it is a paragraph in Planck paper that if you allow curvature, then you get something which is completely look like that the CMB Planck data is not consistent with the flat universe itself. Okay, the original data which was I think in the 2015 and also to some extent 2018. But then, you know, there was a different likelihood code, like CAN-SPEC, you know, then basically now things are shifted back. So some people say it's not serious, it's not important, you know. I try not to get side. But I would say that these are something that one should notice. That, yeah, and if there is really curvature is there, you know, then, you know, that can play a role in all the pipelines which we are basically building up, yeah. Even little bit of that can be important. At the moment, when you do in a parametric way means that you feed lambda CDM model to the combination of the data, zero curvature is consistent with the data. But how much of it is but it's difficult to test the. Of course, there would be some bound on the curvature. I don't think I have any values for that. For example, this is here they assume flatness, I think. Yeah, I mean, a little curvature is allowed, but I'm saying that if one really wants to measure curvature in a completely model-independent way, again, there are ways. For example, we have this way to use strong lens systems and supernova to do that. Something not maybe for now, but if you have like you know, tens of strong lens systems, we can basically have a very high precision estimation of the curvature in a model-independent way. That's a work with I'm sorry, I don't have a supporting slide for that, with Eric Linder and Mikhail Denisenia, 2017 or 18. And there are other groups too. So one can estimate try to have a model-independent estimation of the curvature. But at the moment when we feed different models, usually flat universe is consistent with the data.
So a comment beyond what Bishwait said. I mean, this is just in 1998, I went to Aspen. There were two conferences. One was about cosmology. One was about the supernovae. And that is, interestingly, the supernovae community, which has nothing to do with cosmology, seemed to be totally at loss of how do you even understand the standardization that is happening. It doesn't come from any basic thing. Has that thing at all changed over time? Is there any understanding of this reparameterization that is being done to make these standard candles?
I don't know. I mean, honestly speaking, I don't know, and it is something a bit sensitive that I don't want to know or I don't want to get involved. But if you look at my archive and look at my last paper, okay, maybe there is one recent paper just last week, but the last one in December is in fact about the latest compilation of the supernova data, which to our extreme surprise, we realized that this data give you the likelihood in a very weird, very small value. Right? You know, for 1,550 supernova, we were getting likelihood of 1,400 something. Then I just went to my lecture 3 of the statistic course, which I'm teaching to people about the goodness of fit, literally. And I said, look, this doesn't make sense. I cannot have 1,450 fitting the standard model to 1,550 data points, and I get this chi-square. So we wrote a paper on that, and we wrote it to the shoes people. Then we realized that, you know, they fit to the statistical part of the data, and then they played with the intrinsic dispersion to get the reduced chi-square equal to 1. But then at the end, they added the systematic error to that. So then they have an oversized covariance matrix, which give you the. So if it is a state of art in 2022, you know what I mean. I'm not saying that. And then they were writing. We were going back and forth that, you know, what to do. They were saying, okay, maybe I agree that, you know, it's a very tricky situation. That what should we do? We have a systematic errors. We have statistical errors. You know, Should we combine them or first? But the fact is that yes, a big part of the error budget comes by hand. The intrinsic dispersion we put by hand to get for 1,000 supernova likelihood of 1,000. And then when we add them, then error budget might be oversized or inflated. So I'm saying that this is a stage. This is what is right now, and this is when you talk with the Subir tells you that look, you should not trust them, which I cannot disagree. Yeah.
Yeah. So the other comment I wanted to make, since you talk about systematics in either data set, I mean, this is probably the side.
You should not say in front of
so
any
what is
member.
When one says there's systematics of fitting to CMB data, there are issues, right? So when you looked at the full Planck values versus what you get from high angular resolution, SPT and all that, there were differences in parameter. Right. And if you remember, there was a lot of talk about CMB being not consistent with it.
Right.
And also WMAP gave parameters which were,
high L and low L.
Different, right? Yeah. So and it turned out that so there was a very detailed analysis by Lloyd Knox and all that, which essentially pointed out that this is intrinsic to the data. I mean, the fact that Planck, if you restrict it to WMAP, it will give you the WMAP. If you take the other half, which is the high L, it will give you what SPT is giving. It so happens that Planck has both the things in it, and it gives you another set of parameters. So that is a kind of systematic. But what I wanted to basically point out is that word is the same, but that systematic effect, to my understanding, is a different kind of systematic effect.
I agree.
Than what Vishwajit is talking about, or
No, I certainly agree that I think the way we understand the physics of the CMB and the way it has evolved, right? I mean, it's very solid. With the supernova, as I said, we still don't know the uncertainties which we get. We just put by hand that to get our degrees of freedom equal to the chi-square we get. And if something goes wrong, as I said, it's the latest compilation, it's Pantone Plus. It's not about the 1999. It's just like a paper we put, and we wrote it to them. We wrote to the Adam Rees and Dan Skolnick, and they were very kind. They were responded, and they said, okay, but that's how we can do it. And I agree. I mean, I'm not saying that there is a better. So we proposed something that maybe at the end we should do this again and again. It doesn't much affect on the parameter estimation or model selection, but I would say that still, when we don't understand individually how much is the error budget. So dealing with these things, as I learn more by time, I realize that I don't understand very well how things are clearly done. And it is something which maybe I don't want to also spend so much time on it. Yeah. But certainly we need independent measurements. We need independent measurements.
Okay, if there are no questions, then before leaving, I will just request Professor Tarun to give a small gift as a token of appreciation.
Thank you. And sorry if I exceed the time and discussions went. I usually hate those speakers who exceed the time. But I exceeded the time only 5 minutes, so. Yeah. Okay. Okay, thank you very much. Thank you, Tarun. Yeah. Thank you, everyone. Yeah. Thank you. Okay, thank you. Yeah. Thank you.
Okay, there is a tea outside. I think we can go.
Okay, thank you so much. Yeah.